We are dealing with 1.5 today. It's going to deal with quadratics where we use the square root property. So this one's pretty easy. Y squared equals 16. We just square root both sides. Don't forget the plus or minus 4. What if it said y squared equaled -9? Then this is saying no solution because it only wants real number answers. No imaginary numbers. Why do we call them imaginary numbers? Is it because they don't exist? No, they do exist. Why do we call them imaginary? So, what do we call this? What number line? The real number line. So numbers that do not land on the real number line must be fake numbers or imaginary, just like all of Adam's friends. So where do they land? You can graph imaginary numbers like this. So this is our x-axis, and this could be our imaginary axis. So 4 minus 3i, we could graph it as 1, 2, 3, 4, 1, 2, 3, right there. Well, so on the xy axis, there are no imaginary numbers. But if you wanted to represent imaginary numbers on an axis, you could call the x-axis the real axis, and the y-axis called the imaginary axis. That point right there represents 4 minus 3i. So why did we invent imaginary numbers? Well, it started out as a way to solve all quadratics. So the fundamental theorem of algebra says every polynomial has a specific number of roots. Every x to the 8th polynomial has 8 roots. Every x to the 5th polynomial has 5 roots. But the problem is, sometimes those roots are imaginary. And it doesn't make sense to you why that's a problem, but it is the fundamental theorem of algebra. It is the most basic theorem of algebra. And without it, a whole bunch of stuff breaks. And it turns out that imaginary numbers are used all over the place. They're used in electronics. They're used in complicated trigonometric equations, which is really weird because the equations themselves don't have imaginary numbers in them, but you have to have imaginary numbers in order to use them. So it's kind of weird. If I had, this doesn't really apply, but maybe you'll find it interesting. What if I had x equals 3 minus 2i? That's one of the roots, but imaginary roots always come in pairs. So what would the other root be? If one of them is x minus 2i, then the partner has to be the opposite of this, x plus 2i. Now watch what happens. I'm going to create a quadratic, so I move these over. Oh, that didn't make any sense. So move these over, and I get x minus 3 plus 2i, and x minus 3 minus 2i. Now, when I multiply this together, I get x squared minus 3x. Now, watch this. I'm really lazy. This one and this one are opposites. So they cancel. So I'm not even going to bother writing them down. Right? The negative 3's are not opposite, so this gives me negative 3x. But this one and this one are also opposites. So I'm going to skip it. X times... Oh, I drew that wrong. I'm sorry. It canceled that. Yeah. Yeah. So negative 3 times negative 3 is plus 9. And then this one gives me minus 4i squared. But what is I squared? Negative 1. So really this is just plus 4. So I just created x squared minus 6x plus 13. If I graph that, I've broken it. Look at that. That's new. Never seen that happen. All right. So if I go into y equals, and I graph x squared minus 6x plus 13, what do I know about this graph before I graph it? If the roots are imaginary, it's going to miss the x-axis, right? So I just created the graph of x squared minus 6x plus 13, and the roots of that are x equals 3 plus or minus 2i. So anytime a parabola misses the x-axis, the roots are imaginary. They do exist. And how do I build this equation? I build it using those numbers, just like I did. You move everything to one side and you multiply the two trinomials together and you get x squared minus 6x plus 13. So if you want to build a quadratic that misses the x-axis, you have to use imaginary numbers to do it. There's no other way to do it. Okay? Well, what do the 3 and the 2i have to do with anything? Well, what happens when I do 3 plus 2? I get 5. And 3 minus 2 is 1. Okay? If I flip that parabola upside down, what do you notice? It hits the x-axis at 5 and at 1. Whoa, weird. So let's say I had an x to the 5th. Well, nope, let's have something bigger than that. So let's do... So this has 5 roots. Okay? 1 root. This counts as 2 roots, right? Anytime you bounce off the x-axis, that's a double root. Why is that the case? Well, if I took this graph, if I took this graph and went down, it has 5 roots, right? Well, now how many roots does it have? It still has 5. Well, only 3 of them are visible. And then these 2 roots right here, as I go up, they become a single root, right? So where are the 5 roots? There's 1 here, there are 2 there, and there are 2 there. But what do I know about those roots? They're imaginary. So anytime you have a wiggle above or below the x-axis, that represents 2 imaginary roots. Now, it's not always that visible. Sometimes they're imaginary roots that are hidden in the equation and you can't see them. But if you have something like this, you can guarantee that there are a pair of imaginary roots at least. There might be 4 of them, there might be 6 of them, but there are at least 2. Okay? All right, so what does that have to do with today? Nothing. Okay. So how do we solve this? Well, I could move everything to the left side, but notice there's a v squared term and no v term. So if I subtract 35, and I get 5v squared equals 90, or not, yeah, 90, then I could divide by 5, v squared equals, what is that, 18? Now I take the square root, and I get v equals plus or minus. Does 18 have any perfect squares inside of it? 4, 9, 16, 25, 36, any of those? 9. What's the square root of 9? 3. So 3, and what's left? 2. So what I said was 18 is 9 times 2, and I square rooted the 9, and I get 3 root 2. Now, if you prefer factoring it and circling the pairs of roots, that will work. Okay. Okay, same thing here, just square root both sides. That's the same type of problem. All right. Here, we add 54. X minus 10 squared equals 54. Square root. X minus 10 equals plus or minus the square root of 54. Think about it. Does 54 have any perfect squares inside of it? 9. 9 times 6. So we square root the 9, which gives us 3, and we leave the 6 on the inside. Okay, does anybody not understand that? If you prefer doing it this way, 54 is 2 times 27, 3 times 9, 3, and 3. So we cross off anything that factored, circle the 3's. So 3 root 6. And then we just add the 10 to the other side. So x is 10 plus or minus 3 root 6. Same thing here, but it wants your answers to be decimals. So on the last one, I had 10 plus 3 root 6. I would just type in 17.34 and 10 minus 3 root 6, 2.65. All right. We are going to review completing the square, but I want to make sure you understand why completing the square works. So if I had x minus 4 squared, what does that create when I multiply that out? X squared. So I get 2 copies of negative 4x, and then plus 16, right? And that becomes x squared minus 8x plus 16. Okay. What if I had x plus 3 squared? X squared plus 6x plus 9, right? X minus 11 squared. X squared minus 22x plus 121. Now, all of these quadratics have something in common. There's a pattern that they all follow. All of these are perfect squares, right? In fact, they are the perfect square of that number. Okay, what about the middle term? The middle term is the end of the factor times 2. So we call these perfect square trinomials. Perfect squares meaning they were created using some factor times itself, and trinomials because they have 3 terms. Perfect square trinomials. Now, if you have a perfect square trinomial and it equals, say, 9, it's really easy to solve. So I could just square root, and I get x minus 4 equals plus or minus 3. And then I add 4, and I get x equals 3 plus 4 is 7, and negative 3 plus 4 is 1. Okay. The other way to solve that would be to multiply this out. X squared minus 8x plus 16 equals 9. And now I bring the 9 over, and I get x squared minus 8x plus 7, which gives me x minus 7 and x minus 1. And what do you notice? It's the same answer. So there are two ways to solve perfect square trinomials. Either you just square root from the beginning and solve, or you multiply them together and move that 9 to the other side and solve using factoring. So what we're going to do is force quadratics to be perfect squares. If I had x squared minus 6x plus 5 equals 0. Does that fit the pattern of a perfect square trinomial? No. So if it was a perfect square trinomial, we would have this equivalent to that. Okay? So if it was a perfect square trinomial, what would go inside there? Not 2. It would need to be half of that. Okay? But because it's not a perfect square trinomial, I'm going to move this out of the way. So x squared minus 6x, I'm going to leave a space, equals negative 5. Okay? So what would go in here? Negative 3. And if that's a negative 3, what goes there? A 9. We have just done what is called completing the square. What does that mean? We turned a quadratic that is not a perfect square trinomial into a quadratic that is a perfect square trinomial. But what happens when I add 9 to that equation? The balance is broken. And what happens when there's no balance? A Sith Lord is born. That's what my son told me the other day. So the equation was nice and happy. The right side and the left side weighed just as much, and I just added 9 pounds to the left side. Now the balance is all wrong. So to even that out, I add 9 to the right side. Oh, good. Balance restored. And that equals 4. And now I can solve. Square root x minus 3 equals plus or minus 2. Add the 3. 2 plus 3 is 5. And negative 2 plus 3 is 1. Those are my roots. That is called completing the square. So we go back to Alex. So is this a perfect square trinomial? No. So, kind of dumb, but it wants you to pick the correct one. It's going to be the bottom one. And then solve it by completing the square. So we need to move the 19 out of the way. X squared minus 10x, leave a space, equals negative 19. And x minus 5 squared, so this is a 5. And what would go here? 25. And if that's a 25, then I need a 25 over here, which gives me a 4. And now I can solve. Square root x minus 5 equals plus or minus 2. Add the 5. X equals 7 and 3. Wait a minute, that's not right. Oh, it's a 6. Okay, I'm sorry. Let me go back. I did that wrong, but let me go back here. So, is there another way to get this? Sure, look at the original equation. Does it factor? So it factors into what? X minus 5 and x minus 1, which are going to give me 5 and 1. So why did I teach you a new method when there's already a method that works and it's easier? Sometimes it doesn't work. So if we had x squared minus 6x minus 5, does that factor? It wants to, right? Can I use 5 and 1? Negative 5 and negative 1? Does that work? No, because they do not create a positive 5. All right, so let's change the sign on one of them. Now I don't make a negative 6. So this quadratic is not factorable. What does that say about its roots? They could be imaginary or they could be irrational, right? They could be something like 1 minus the square root of 3. So if your quadratic factors, then the roots are either whole numbers or integers or fractions. If a quadratic factors, then the roots are rational. There's some version of a fraction. If a quadratic does not factor, the roots are either imaginary or irrational. So before I made a mistake on this one, oh, I lost it. But does this factor? Are there factors of 19 that add to be negative 10? Well, 19 is prime, so my only option would be 19 and 1. Can you create a 10 using 19 and 1? No. But we ended up with x minus 5 squared equals 6. And now I can square root both sides. X minus 5 equals plus or minus root 6. And add 5. And there we go. Solving using completing the square will always work. Every single time. Factoring only works if the answers are fractions. Okay? Oh, so the only difference here, this one wants decimal answers, and this one wants exact answers. So 5 plus or minus root 6, that's the exact answer. If you plug those into your calculator, those will give you the decimals. Do you want to see another completing the square problem? Yeah? Okay. So is this a perfect square? No. So x squared minus 6x, leave a space, get rid of the constant, just stick it on the other side. What goes in here? X minus 3. Negative 3 times negative 3 is 9. So I add 9 over here, and I get 3. Square root x minus 3 equals plus or minus root 3. 3 plus or minus root 3. Got it? Okay, get to work.